Hi everybody. We're Ivan and this is Wayve, and so today we're excited to share with you some work on using foundation models as imagination engines for robotics. So the big question is, why is human-level embodied intelligence so hard to reach for robots? And toddlers can already learn to grasp a new object with just a few seconds of experience. I mean, just look at this little guy, right? Seems innocent enough, but here's what he's hiding. When humans are born, they're not exactly a randomly initialized set of weights. You all are the product of millions of years of evolutionary optimization. So that's billions of episodes of experience in complex environments, and that's why humans have such great spatial intelligence. The problem for robotics is this. For most of human history, we haven't been recording this visual experience, so we can't train a robot on that same data as humans have been trained on. Fortunately for robotics, we did recently start doing this, and that's essentially what the internet is. It's a large-scale source of human experience in images, languages, and video. So we have these foundation models like Clip from OpenAI, and they're trained on millions of captioned images from the web. This is a huge amount of data that's lossily compressed into just 2 gigabytes or so of model weights, which you can run on your phone. So that's pretty amazing. But these models also have some useful properties specifically for us in robotics. First, the training data covers a broad range of objects, scenes, and tasks. And this is useful if you want to make a generalist robot. Second, this training data exists anyway, so we might as well use it. So millions more images are being shared online every day, and we don't need any extra human effort to collect that data like we do when collecting robot demonstrations. Okay, so how can we use these foundation models in robotics? There are many ways, but we'll cover 4 of them in this talk. First, we can use them essentially as reward functions. So you give it a state, and it tells you how good that state is. Second, we can use their natural language processing abilities for task planning. Third, we can use them to understand a scene and break it down into objects. And fourth, we will also see how we can use visual features from foundation models in our robotics pipelines as well. Okay, so the actual problem we want to address with this method is this. Imagine you ask a future robot, please tidy my kitchen. Okay, well, before the robot grasps anything, it should probably figure out what the goal state is. So for each object, where should I put it? And to address this problem, we're going to use the web-scale visual prior of diffusion models like Elahe. So you give it a text prompt and it generates an image. I'm sure you've all seen some of these before. And we found that if you give DALL-E an image of a dining table and ask it to place a spoon into this scene, it generates that spoon in a semantically correct pose. And it is the same for a computer mouse as well. So this suggests that foundation models have a strong visual prior for what a natural state looks like. So the question is, can we use this for robotics to imagine a good goal state zero shot for these tasks? And this is what we explored in our paper called DALL-E-Bot with Ed and Vitalis. The key idea is very simple, it's basically this. So first the robot detects all the objects in the scene, and then it prompts DALL-E with this list of objects, which generates an image with a human-like arrangement of those objects. The robot then rearranges the real scene via pick and place to recreate this generated arrangement in the real world. And in this video you can see the robot performing this rearrangement. So here in the top right we've got the goal image that's generated by DALL-E. In the bottom right we have the final arrangement that the robot's going to create. And you can see basically what it needs to do is it needs to match between the generated image and the initial state of the real world. It needs to figure out by how much to move each of the real objects to match this arrangement. And then we use motion planning to kind of perform this pick and place and put the objects into their goal poses. And notice we don't need to do any training. This is fully zero shot. We just use this kind of web scale visual prior to figure out what a good goal state should be. And the method is kind of fully autonomous as well. So we don't need any human demonstrations or human effort. Okay, so here you can see some more goal images that have been generated by our method for different scenes. So you can see it works on a dinner table, an office desk, and a fruit arrangement. And you can see that this kind of web-scale visual prior from the diffusion model leads to a diverse set of natural and human-like goal states without the user needing to manually specify what state we're trying to reach. And this is probably because these tidy states are the most common modes in web-scale data. So here are just a couple more interesting details about how this works and why. So, okay, what the robot needs to do is it needs to match kind of the real knife to the generated knife and the real spoon to the generated spoon. And this is quite a hard object pose estimation problem because like they're not even the same object, right? So even though they're different in kind of RGB space, this is like the real object and the generated object, we found that if you look at the semantic feature maps, so for example, you put this image through ImageNet, you actually get pretty similar semantic features for generated images from diffusion models as you do from real images. And this is quite an interesting finding. And this means that if you can do this kind of pose estimation, even though it's a generated object that you're using as part of that matching process. So that's why semantic features from visual foundation models can help cross this domain gap. Our method can also use in-painting from diffusion models to take into account objects that have already been placed by the user. So you can use an in-painting mask to tell DALL-E, okay, you can change these pixels, but you gotta leave these pixels alone. So when you ask it to put a fork into this scene, you can see it's conditioned on what's already there to put the fork in a sensible place. So this means that you can do a kind of collaborative human-robot rearrangement. So far, this works pretty well, but it's limited to 2D tabletop scenes. And the next question is, what if we want to solve a 6-degree of freedom task? For example, like putting this pink bottle on that shelf. Well, for this, I'm going to hand over to Wayve. He's going to tell you a bit about our next paper, which is called Dream to Real.
Hi, thanks Ivan again, and also thanks to our joint author like Ignacio and Professor Ed. So here is our Dream to Real work. So the key idea here is, first, the robot will autonomously build an editable object level nerve here. This allows it to render where the scene looked like if the object were arranged differently. And next, it evaluates these sampled arrangements with the visual language models to see which goalposts best match the user instruction. And finally, the robot will use the goalpost to execute the rearrangements in the real world. All right, as you can see here, the nerve can train in just a few seconds and gives us photorealistic renders of object in any given poses. And next one, for each sampled object pose, we render the scene as if the object were in that pose. For each rendered image, we compute the clip similarity between this image and the user's instruction here. This can be done super efficiently in parallel for many sampled poses, and we choose the highest scoring arrangement as the goal state. All right, then the robot uses the pre-trained DexNet to grasp the object. Since the robot has already built these 3D representations, so we can use this for collision avoidance during our motion planning, as the robot places the object into its goalpost. All right, so here is our experiment setup. We evaluated on 10 different rearrangement tasks across 3 distinct real-world scenes, including our shopping scenes and the pool table scene, and also a 6-stall shelf scene. Here are some conclusions. So first of all, we want to kind of answer if this vision language model can understand complex spatial relations using the web skill priors. As you can see from this figure, the first column shows the initial state of our scenes, and these are different tasks. The top one is put the black 8 pool bowl to make it a triangle shape, and the second one is to make it an X shape. The middle images shows the final VLM heat map, and the lighter the color means the higher the score, and the red dot here means the best goalpost, which corresponds to these final renders of our imagined goal state. As you can see here, the score is high around the correct place to accomplish the desired shape, which means the vision language models has spatial relations priors. Also, we'd like to investigate if it can perform 6-stop tasks, or do we need multi-view data here. The red top table here shows the 3 different tasks in our shelf scene. Just a quick reminder back, this is our top shelf scene, and we gave it 3 different tasks here. For example, we want to put this red bottle to make the 3 bottles in the line, or to put it in front of the book, or to put it near the plant. So as you can see here, our method achieves over average 80% of success rate here, which means the VLM does a pretty good job here. And moreover, we also did this ablation on single view or multi-view inputs, and the bottom right table here shows the multi-view really gives some more robustness for the system. Here's another quite interesting takeaway. Compared to the previous method, as Ivan just said, the DALL-E bot, the majority difference here is how to use the foundation models, whether to use it to evaluate or predict. So the question here is, which one is better? These 2 figures shows how the goal image look like if we just ask the foundation model to predict it. So for example, here, if we ask it to generate like apple inside bowl, sometimes it will generate more like random numbers of apples and random numbers of balls on the table. Also here in the pool table scene, it will generate some random things. So the quick answer here is somehow evaluate states might be slower, but more controllable than the directly predicting goal state. All right, so let's summarize some strengths and limitations of distributed real world. So first of all, this method uses vision language model 0-shot, so it does not require any example arrangements or further training. And second, it can conduct in 3D scenes with fully 6-stop poses. And third, it uses VLM, because it uses VLM to visually evaluate whether a rendered arrangement looks correct or not. It is not bottlenecked by having to convert the whole scene into some text description or coordinate description. And as for the limitations, first of all, of course, the running time is a huge limitation here, particularly for some lower tolerance tasks where the more denser sampling is required here. But this one can be improved by iterative sampling and scoring. Dream2 also inherits some limitations of the vision language models, for example, the back of words behavior, as you may know. However, this also means that Dream2 will improve as vision language models continue to improve. All right, so last, I want to give some insights about what's next in web scale priors for robotics. So here are some of the bullet points. So first of all, rather than directly predict the goal pose, maybe if we can somehow generate a compositional goal image based on the initial scene and relevant object, then we can match the moved object as in DALI-bot to define the goal pose. And second, video generation model is also a way to define the goal pose and next state. Similar as some prior works, for example, the SUSI, if you know, where for each step it predicted the next goal image and mapped actions based on that. So if large video generation model can work properly, it can give consecutive sub-goals and we can easily extract actions from them. And third, in some RL settings, vision language models can also serve as a generalist, controllable, and shape the reward function. And lastly, image to 3D generative models can also be super useful in robotics, which is also something we are currently investigating. Most of the time, we cannot really reconstruct the whole scene or object due to the lack of image inputs or some occlusions here. So, however, these image to 3D models can provide additional information about what the object should look like from these missing views. So this is one example, amazing work called Asher Knight, which given different any numbers of input reference view, it can generate the inquired novel view from outside, from the model. And that's really important if we want to somehow augment our current data to some novel views that we never actually collected. And yes, that's pretty much. Thank you very much for this, and happy to take any questions.
Questions? Any questions? We have time for one.
Thank you very much for the talk. Just a quick question. So by using the LLM to generate the target goal, that means that you're not taking into account personal preferences or things like that. Do you think this could be extended to that end?
Yeah, it's a good question. Yeah, definitely. So one way you can do it is you can include this in your language instruction. So here, when we're generating these kinds of goal images of let's say the dining table from the diffusion model, we don't tell it to generate like a neat arrangement. We just tell it the list of objects, and it defaults to a neat arrangement because this is the most common one that's prevalent in kind of the web scale training data. Now, if you want to force it to generate a specific state, probably all you need to do is add that to the language instruction. So if you said something like put them all in a row, it's more likely that it will do it. So that's probably quite an easy way to condition it on individual preferences.
All right, thanks a lot.